Is it started? Yes, a very good morning to all of you. Am I audible and visible to everyone? Am I audible and visible to everyone? Yes. Okay. How did you write your test? Electron affinity, absolute value they were asking, it is negative. I made you write consider to be 0. That means basically they do not want to accept it. But if at all they are asking about the absolute value, you have to give negative only. And that is very well clearly mentioned in the notes. Right. Okay, so how far I think we have covered in our portion last class? How far we have covered? I think octet rule we have finished, right? Octet rule we have finished. Okay, fine. Limitations also done. Okay, fine. So today we'll be starting off with the Fazan's rule. So without any further delay, let us start off the session. So Fazan's rule. Wait. Chat. Okay. Now, basically, whenever I say that I have got any kind of, ionic compound, okay, so I will not be ever able to say that that particular ionic compound is having 100% ionic nature associated with that, okay. It might have basically some amount of covalent character associated, right? To explain that only, basically this Fazan's rule was given. Okay. Similarly, if at all I am having a covalent compound, even I cannot say this is 100% covalent. It will have certain amount of ionic character associated, right? And basically you read about something kind of, dipole moments, some polarity which explains you that, right? So similarly, like 100% ionic, 100% covalent, that is only like kind of very ideal cases which do not normally exist, right? So Fazan's rule is for explaining the covalent nature which exists in ionic compounds, okay? Now, the other thing is, let us try to understand this Fazan's rule. And see, when I'm talking about ionic compound will be made out of what? A cation and anion, right? They are basically getting ionic, like there is electrostatic interaction which is between them, and hence we call it as ionic compound, right? Now, the thing is, let us say I have got cation and anion, right? Now, the thing is, cation in general is smaller than the anion. Okay, so let us say that I am putting a smaller sized cation here and a relatively bigger size anion, right? Now the thing is, till the time they are very, very far away from each other, there is no problem, okay? There is no interaction among them. But the moment they try to approach each other, so there are certain interactions which start developing between them, okay? What are those interactions which you can think of? There will be like attraction between the nucleus and the electron of the other one. Similarly, like this also. These are the attractive interactions which are there. And similarly, you'll have this electron-electron repulsion and internuclear repulsions also existing there, right? But still, if they are trying to come closer, still approaching closer to each other, that means still this force of attraction is dominating there, okay? Now, let us try to see how the covalent character is introduced here. So, let us say I am having this particular cation, right? A plus, and I am writing this as a bigger anion, right? Now, if this cation is not nearby this particular B minus, the electron cloud around it is going to be symmetrical, okay? Now, the thing is, the moment this approaches it, so what happens? A plus, the thing is cation, here A plus, the nucleus of this particular cation is having good hold on its own electron. That means higher force of attraction is being felt by the valence electron of that particular cation itself, right? So what will happen if it is approaching near to this anion? So it will be, this particular nucleus will be able to attract that particular electron cloud of B minus towards itself. So the symmetrical electron cloud has become unsymmetrical, right? And this distortion of electron cloud only we call it as polarization. And now it gives you a feeling that the electrons are kind of being shared between these two, and hence little bit of covalent character has come. That's what is explained by Fazan's rule. Okay, so you understood what is the meaning of polarization. Polarization is nothing but the distortion of the electron cloud of the anion by a cation. That is basically polarization. Now there are two more terminologies. One is polarizing power, right? We'll write the notes, don't worry about it. And another one is polarizability. Now, when I talk about polarizing power, so power you always apply on someone else, right? So here, out of these two, who is causing the distortion? It's the cation, right? Now, the thing is, you might think that is this distortion only one-sided, not the anion is able to do? Anion is also able to do, but the extent to which it does is very, very negligible. That is the reason we say that, like, more influence of cation on the electron cloud of the anion, right? Now the thing is power. So how easily it is able to distort that electron cloud of the anion towards itself is the polarizing power of cation, right? Polarizability, this is the term related to the anion. How easily that particular anion is letting its electron cloud undergo distortion. That is basically polarizability, okay? So now let us write down all these terminologies. You need not draw this diagram, you can draw this diagram as such. So I'm going to write down few things here. An ionic compound is not 100% ionic in nature. It has certain amount of covalent nature associated with it, and this is explained by Fazan's rule. Okay, that's what we read this Fazan's rule for. Okay, then we'll write down the definition for polarization. So we can write when cation and anion approach each other, then the cation pulls the electron cloud towards itself, and this distortion of electron cloud of the anion by the cation is only polarization. So this distortion of the electron cloud of anion by the cation is known as polarization. Right. So make sure you are writing this definition, and then I'll show you the diagram so you can copy this out. Hopefully you people have written this. Okay. Below this only you can draw this particular diagram of polarization, the phenomena. Need not draw this diagram. This is only to tell you what are the interactions which may exist if the cation and anion are approaching each other. I hope it is done. Now let us go for polarizing power. So we can write down the ability of a cation to distort the electron cloud of an ion is known as polarizing power. Okay. Next term is polarizability. Now when I talk about polarizability, it is the ease with which a particular anion undergoes distortion by a cation. With which you can write down with which electron cloud of a particular anion undergoes distortion by a cation, right? After this, we'll see the factors which are responsible for which affect the polarizing power of cation. Once you finish writing this, and then we'll proceed further. Okay. Now, let us see what are the factors which affect, and in fact now for the polarizing power, somewhere I may also write down this short form which is PP. It is not a standard short form, but only to save on some time rather than writing the entire thing. Okay. So factors affecting polarizing power of cation. Okay. So in this case, the very first one comes out to be size of cation. Right. Now the thing is, I say that the polarizing power is inversely proportional to the size of cation. Can you think why we are saying so? Why we are saying so? Now the thing is, if at all suppose I give you one smaller cation like A plus, another B plus is there, which is again even more smaller than this. So more smaller size, that means on its own electron it will have nice hold of electrons. That means force of attraction felt by that particular electron is going to be more. And if any other bigger size anion comes near to it, so what is going to happen? It is going to easily distort or else attract the electron cloud of that particular anion towards it. So that's what is we are writing, that if the size decreases, polarizing power of that cation increases. So for example, if I ask you about Li plus and Na plus, polarizing power of whose is greater? Li plus, because of the size factor. Similarly, beryllium plus 2, Mg plus 2. Accordingly, we can go for, right? Okay. Now, next one is charge on cation. And here it is seen polarizing power is directly proportional to charge which is present on the cation. See, the thing is, if at all I give you A plus and A plus 2, where do you feel that the force of attraction is going to be more? Effectively, more nuclear force of attraction. Definitely, it is going to be more in case of A plus 2. If it is more there, so the thing is, this will be easily able to distort the electron cloud of the anion, right? So, for example, if I say Fe plus 2, Fe plus 3, whose polarizing power is going to be more? Definitely Fe plus 3, right? Sn plus 2, Sn plus 4, polarizing power of Sn plus 4 is going to be more, okay? So please write down these two factors, then we'll proceed further. Yes, I hope it is done. Okay. Now the another factor which is there, that is electronic configuration. So in case of this electronic configuration, first one we are having inert gas configuration, and this all of us know that if at all inert gas configuration, how many electrons should be in the valence shell? Just before this we have studied about octet rule, no? So basically there should be 8 electrons here. So we are having Ns2 Np6, right? Are you able to see 8 electrons here? Now if at all I write about Na plus, so we'll be writing like this only, 1s2 2s2 2p6. So it is having configuration like this. Now what all ions could have inert gas configuration? You can have Na plus, K plus, Rb plus, Cs plus. You can also have basically Mg plus 2, Ca plus 2, strontium plus 2 and barium plus 2. Right? So at present you just understand, okay, these are having the inert gas configuration, and here you are having S and P, right? So we know that these electrons, or else S and P, they have got good shielding effect. So they'll be able to shield the nuclear force of attraction of this particular cation. So it will not be able to reach out towards the electron of the anion. Getting it? Because of good shielding effect of S and P, right? So we are going to write down the cations having inert gas configuration have low polarizing power. Okay? Getting it? So you must understand, okay, there is like inert gas configuration. It should have 8 electrons in the valence shell, which you are able to see. And they are having low polarizing power. Okay? Write down this one, then we'll proceed further. Yes, are we done writing? Okay. Now, the another configuration which is there, that is pseudo inert gas configuration. In the pseudo inert gas configuration, basically we should have Ns2 Np6 Nd10, right? So how many electrons we are having? You must know this. You are having 18 electrons in the valence shell. Let us say, suppose if I write for Cu plus or else Zn plus 2, the configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s. 2 electrons we have removed from 4s itself. See, the thing is, this is 4s1 3d10, this is 4s2 3d10. So electrons will be removed from the outermost shell only. So that is gone. So we are having like this. So are you able to see this is having this kind of configuration, right? That is pseudo inert gas configuration. Now think who all can have this kind of configuration. All the members of copper, that means that particular group, 11th group, and all the members of zinc, right? So you are having Cu plus, Ag plus, Au plus. You are having Zn plus 2, Cd plus 2, and you are having Hg plus 2. All of them, they are having this kind of configuration. And in fact, you don't need to remember, exclusively, because the thing is, copper, Ag, Au, you remember that they are basically the coinage metals. You are having zinc, cadmium, mercury, they all belong to the same group. Getting it? Now the thing is here, because of this d electrons which are there, they are not going to shield the nuclear force of attraction very nicely of its own cation. So what is going to happen? That particular nuclear force of attraction can easily reach out to the electron cloud of the anion, right? So we can say the cations having this configuration have high polarizing power. Have high polarizing power. So please write this out. Yes, finish writing it, then we'll proceed further. Is it done? Writing this? Okay. Now let us go for the third kind of configuration which we have, that is non-inert configuration. And in this non-inert configuration, basically you will be having ns2 np6 nd10, that means 18 electrons, and apart from that you are having n plus 1 s2, right? Now the thing is, you are having this as 18 plus 2, but you must understand this is like outermost shell is having like s subshell we are talking about, okay? N and n plus 1 is there. Now in this category, basically all those ions will come for which you've already, like I've taught you about the inert pair effect, right? So in group 13, which particular element which is there? Thallium plus 1. Remember? As such, it should be thallium plus 3, but thallium plus 1 is more stable, right? So it will have this kind of configuration. Similarly, in group 14, you are having Pb plus 2, which is there, and in group 15, you are having Bi plus 3. So all of them, they are having this kind of non-inert configuration, right? Here also you are having d electrons, but the thing is, outermost subshell is basically having s, which has got relatively better shielding effect in comparison to the pseudo-inert. So here also there will be like shielding, but definitely it is better than that pseudo, right? In case of inert, that is like best shielding because S and P both were there. Here only S there, right? So because of that, here polarizing power of this is going to be relatively higher than the inert gas configuration, but lesser than the pseudo inert, right? So ultimately we have to just remember the order basically. So polarizing power order is pseudo inert gas configuration, that is maximum, over then non-inert gas configuration, and then you are having inert configuration, right? So this is the order which you must remember. Even if at all you are feeling that something is little bit difficult, do not worry about it. Just remember, for pseudo inert gas configuration, what are the cations which are like having this kind of configuration? Non-inert we have just seen, right? All those which we have already learned in inert pair effect, and you are having inert configuration that you need not remember, right? So for example, if I ask you the polarizing power of Zn plus 2 and Na plus, you only tell me which one will be more. If it is first, then it is thumbs up. Correct. So it should be for Zn plus 2, right? Then if at all I give you Pb plus 2 and Ca plus 2, if it is second, then thumbs down. In this case, you are having for Pb plus 2 only because it is non-inert gas configuration. Getting it? Again, if at all I write down Hg plus 2 and suppose Na plus, out of this you are having pseudo-inert gas configuration, and for Na plus you are having basically inert configuration. right? So inert gas configuration. Here I have not written completely. If you want, you can write configuration. Finish writing this. Then we'll proceed further. Yes, I hope we are done writing about it. Then I'm just writing down one note. BCl2, BH2, AlCl3, even the dimer of it, which is Al2Cl6, AlBr3, dimeric form of it, Al2Br6, you know, etc. Just few of them I have written, you know, are covalent compounds, you know. They're covalent compounds. Normally what we think, it is a metal and a non-metal, so it should be a basically ionic compound. But here, because of the high polarizing power of B+2, Al+3, these compounds are covalent in nature. Okay. Now next we are going to see polarizability of anion. That is going to be directly proportional to size of anion, and it is also directly proportional to charge of anion. Now you try to understand polarizability means for a particular anion how easily it is letting its electron cloud gets distorted. If it is very easy process, that means any cation which is there, it should be able to attract that electron cloud nicely. And which electron cloud could be attracted nicely? Which is loosely held by its own nucleus of the anion. So if at all there is like something like A minus and you are also having B minus, but B minus is bigger in size. A minus is little bit smaller in size. So whose electrons are, you know, kind of away from its own nucleus? Definitely in this case, B minus. So for that reason, any cation which is approaching it, or else when a particular cation is approaching this anion, it will be very easier for it to have that electron cloud attracted, you know, from this particular B minus anion. That's what is size of anion factor. Now if I give you A minus and A minus 2, okay, so the thing is here, in this case, I am saying that it is easier for any cation to distort the electron cloud. Reason being minus 2. Minus 2 means what? There is already higher interelectronic repulsions, right? They're already fighting among each other. So any person can take advantage of it, and that the third person who is here is basically the cation, right? So cation will be able to easily attract or else attract the electron cloud from higher negatively charged anion, okay? So that you must understand. So if at all I give you example and I ask you for the polarizability order, Cl minus, Br minus, definitely it is going to be Br minus. And if at all I give you something like O minus 2 and N minus 3, then according to charge, it has to be second one, right? So please write this particular slide and then we'll proceed further. Straight away, we are going for the questions now. What kind of question you can expect from the Fazan's rule? Yes, I hope it is written. Yeah. Now next is, if at all we talk about polarization here. So polarization is basically the phenomena of distortion of electron cloud of the anion by a cation, right? Now the thing is, polarization, we are going to say, we are just going to club all the factors which we have recently learned. That means, what are the factors which affect the polarizability or the polarizing power, right? So here I can say this is directly proportional to charge on cation and anion. It is directly proportional to size of anion, but it is inversely proportional to size of cation. Right? Now you try to understand, if at all I am saying that charge of the cation is high, then it will be able to easily attract the electron cloud towards itself. That means more polarization. Similarly, if at all the charge on the anion is more, so in that scenario, basically, it's easier for a particular cation to distort the electron cloud of such an ion, because already they are fighting among each other, repulsion is there. Now, second factor, size of an ion. If the size of an ion becomes bigger, right? So in that case, its own electron is slightly far away from its own nucleus, right? So because of that, less nuclear force of attraction from its own nucleus, that means from its own ion. So what is going to happen? A cation which is smaller in size will be able to easily attract the electron cloud of such an ion, and that's what is reflected here. So if at all it is more polarization, that means more distortion of the electron cloud. So we say it is more, it is representing more of the covalent character. And if more covalent character, then definitely we are going to say that the ionic character is going to be less. So we can write down one statement here. Extent of polarization. If this extent of polarization increases, that tells you that basically covalent nature, that also increases. And what about ionic nature or character? That has to decrease. Getting it? So please write this down, and then we are heading towards the questions basically. Yes, I hope it is written. Okay. Now let me give you some questions here. Arrange the following in the decreasing order of their covalent nature. First one is LiF, LiCl, LiBr and Li. Second is beryllium chloride, magnesium chloride, calcium chloride. Then you are having strontium chloride. Next you are having NaCl, MgCl2, AlCl3. Next you are having, suppose, AlF3, Al2O3, Aln, ZNS, PBS. One more example I am writing here. HgCl2, PbCl2 and let us say CaCl2. So identify the order. I'll just discuss after few minutes here. Once you are done, kind of arranging on your own, then you can let me know. I hope it is done. Yes or no? See, in the first case, Li plus cation size is like cation is constant, fixed. Only thing is anion size is increasing, F minus, Cl minus, Br minus and I minus. So if anion size increases, more polarization is possible, right? More polarizability and hence covalent character is going to increase. In other case, anion is fixed. What is happening to the cation size? B plus 2, Mg plus 2, Ca plus 2 and Sr plus 2. Size of the cation increases, polarization decreases and hence the covalent character decreases. Now the examiner can also ask you about, ionic nature also. So it will be reverse order. Okay. NaCl, MgCl2 and AlCl3. So here you are having Na plus, Mg plus 2, Al plus 3. Cl minus is fixed. Now we will decide by the charge. Higher is the charge, higher is the polarizing power of that cation and hence it will cause more polarization. Now coming to these, right? What you are having is Al plus 3 is fixed here and you are having F minus, O minus 2 and N minus 3, right? So again, according to the charge we are going to decide. So higher charge on the anion, easily its electron cloud can be distorted. Now next is ZNS and PBS. So among these two, this is having pseudo inert gas configuration, another one is non-inert gas configuration. Similarly, HgCl2, PbCl2 and CaCl2, the order will be like this only because this is pseudo inert, this one is non-inert and that one is inert gas, right? So I hope this is clear to all of you. So these kind of questions, very simple questions which are there. So you must remember what are the factors which are affecting polarizability and polarizing power, and eventually you will be able to understand what is causing more polarization, right? So I hope this is clear to all of you. Now let us proceed further towards the next topic, that is Lewis representation. Lewis representation of the species containing single central atom. Okay. Single central atom. Right, so we are just going to write down the rules now, right? And all of you must write. The thing is, I'll explain you with the help of few examples afterwards. That means once we just write down all the rules, we'll be able to understand them. So few example, I'm going to do, few example you are going to do. Okay. Now, first one is identify. Now for central atom, I'm going to use C dot A. Identify central atom. Generally, atom present in less number or having less electronegativity or having high covalency is taken as central atom. Yeah? Now the thing is, if at all I ask you something about covalency of carbon, Now, I think we have already discussed about this term covalency, but the thing is, at that time, I have given you the kind of structure which was there. So you just counted down the number of covalent bonds which were there, and hence you defined it. Okay. Now here, if at all only for a particular element, you need to have the idea about the covalency. Ultimate idea is that only, that covalency is the number of covalent bonds formed by a particular atom. Now, the covalent bonds, basically they are formed by the sharing of unpaired electrons, right? So, how many number of covalent bonds a particular atom is able to form, that will depend upon how many number of unpaired electron it is having, right? So, basically I can write down, this is number of covalent bonds formed by an atom, and that is equal to the number of unpaired electrons present in ground state or excited state of the atom. So GS and DS is ground state or excited state. So for example, if I talk about carbon, carbon is 6. If at all I write down its ground state configuration, it is 1s2, 2s2, 2p2, right? So here you are having 2 electrons here, 2p2. So how many unpaired electrons? 2. So the covalency here is going to be, covalency is 2. If at all I go for the excited state, that means I will be exciting one of the electrons from 2s to 2p. So it will become 1s2, 2s1, 2p, 3. Now the covalency will be 4. So maximum covalency is 4. Getting it? So that's how we are having covalency as 4. Right? Do one thing. You finish this and then we'll proceed further. Once you're done writing, let me know. Okay. Now, second point, let us say draw the Lewis dot symbol of the central atom, right? Then next is with hydrogen, fluorine, chlorine, bromine, iodine and O minus, always make single bond with central atom. With oxygen atom, make double bond with central atom, right? Then use the appropriate number of lone pair of electrons to complete the octet of surrounding atom. Now here you must understand, basically if at all I am having hydrogen, it is having on its own, it's having one electron, right? So it just need one more electron so that it can achieve the configuration of helium. So that is the reason if one bond is formed, because only one more electron is required. So one more electron if at all brought by some other species or atom, it will be fine. Fluorine, chlorine, bromine, iodine, all the halogens, they are having Ns2Np5. They are just one electron short from achieving their noble gas configuration. So they will also be happy with one single bond. Now when it comes to O minus, right? So in the valence shell, there are 6 electrons of oxygen, right? If it all minus, that means you have given one more electron. That means it has become 7. So how many electrons it is short of for attaining that noble gas configuration? Only one. So that is the reason with O minus, we are going to make single bond with the central atom, and with oxygen, we are going to make double bond. Oxygen, that means neutral one. Okay. And this one you need to take care that, because normally what happens is we forget about the surrounding atom, right? So for the surrounding atom, once we have placed everything, then you have to just count or else put the lone pair of electrons in such a way that their octet is complete. Okay. Now, let us proceed further. If negative charge is present on species and oxygen is also present in species, then assign negative charge to oxygen. In all other cases, put positive or negative charge on the central atom, right? So first write down these points and then we'll proceed further. Yes, I hope we have written this. Yes. Then next is never violate octet of second period elements and check the formal charge of all the atoms present in species. So we are going to write down the formula here, that is sum of formal charge of all atoms in the species is equal to total charge present on the species. So at present, I'm just going to write down the formula of that formal charge. We'll understand that with the help of the questions only, right? So at present, you just write down the formula, okay? So you are having formal charge here. So I can write that as QF. That is equal to number of valence electrons in central atom. V is valence electrons, okay? Minus total number of non-bonding electrons minus half of total number of bonding electrons. Right? Now the thing is, when I say total number of non-bonding electrons, that means you have to identify electrons present in lone pair. And here this means the electrons which are present in bond pair. Right? So basically, you don't have, suppose if I say that I've got one lone pair of electrons, so I have to report that I am having two electrons. If at all I say two lone pair of electrons, I have to say it is four electrons which are there in those two lone pairs, right? Getting it? So you don't have to report the answer in terms of pair, you have to report the answer in terms of number of electrons, okay? Finish this off and then we'll proceed further. Yes, I hope we have finished writing it. Now let us proceed towards few examples here. Suppose if I talk about CH4, which is the simplest example, right? And definitely you remember you can never have hydrogen and fluorine as the central atom, right? Now, in case of this central atom is carbon, right? Now the thing is, how many valence electrons? So that is the first thing, identifying the central atom. After that, what you have to do? You have to draw the Lewis dot symbol, or else you have to represent the number of electrons around this carbon. That means valence electron, how many? 4. So I have put 4 dots, right? Now, the thing is, with hydrogen just need a single bond, because the thing is hydrogen is surrounding atom. So just put a single bond and finish off the structure of this molecule. Now the thing is, I cannot have the octet around hydrogen because it can only have 2 electrons according to that helium corresponding to that. Now let us check the formal charge. Formal charge on carbon is equal to how many number of valence electrons? 4. Are there any lone pair here on carbon? No. So no, total number of non-bonding electrons is 0 minus half of how many bonding electrons? There are basically 4 bonds. So in those 4 bonds, each bond is having 2 electrons. So bonding electrons I am having 8. So I'll be able to write 4 minus 4, which is equal to 0. Right? And in fact, if at all, the thing is, there is one more method by which you can, kind of calculate this formal charge without the usage of this formula. What you have to do is, earlier you understand that these 2 electrons are equally shared between them, right? They were good friends. Now, there's they have become turned enemies, right? So what you do, you just break this bond equally like this, in such a way that this electron is taken away by the carbon and this hydrogen is having its own electron. So they are saying that whatever electron you have brought, you take with you, and whatever electron I have brought, I'll take with me, right? So basically now only for formal charge we are doing it, mind well. Only for finding out the formal charge. Otherwise we don't. So how many electrons you are able to see around carbon after breaking the bond for the calculation of formal charge? There are 4. Now there are 4 electrons around carbon here. Just compare this with how many number of electrons should have been there in the valence shell of carbon. So group 14 member, it should be 4. So there is no difference. So that is the reason formal charge will be 0 here. For hydrogen also you can check, there is only one electron with it and there should be only one electron in its valence shell. So again, the formal charge on that is going to be 0. So that is the reason 0 plus 0. We are not writing anything, right? Now let us say I'm having another molecule or species like CH3 minus. Now whenever there is a negatively charged species, first you identify whether oxygen is there or not. Right? Because if oxygen is there, I need to give that negative charge to the oxygen, right? If oxygen is not there, so what you're going to do is, this negative charge is being counted with whom? It is being counted with carbon electrons only, right? So basically what I'm going to write down, electrons around carbon, that is equal to valence electron of carbon plus negative charge means plus the charge which is there. Are you getting it? Had it been the case -2, then I would have written +2 here, because minus in chemistry is extra electrons there. So how much I'll be getting? 4 plus 1, which is 5. Right? Now these number of electrons you are supposed to show around this carbon. So 1, 2, 3, 4, 5. Right? Now what you are having, just 3 hydrogens. So with 3 hydrogen, make this bond. Able to see this? And simply put this particular -1 onto this, on the central atom. Remember that? Now the thing is, this -1 you can check, this is basically the formal charge of it. If at all here I am having, you just break this down. How many electrons around carbon? 3 and plus 2, 5. How many should have been there in its valence shell? 4. So 1 extra. So that is the reason -1. Are we able to understand this? Now suppose if I talk about CO3 -2, suppose. This is a negatively charged species and you are having oxygen here. Okay. Now in this case, what you have to do, you have to give that negative charge to the oxygen only. Right? Are you getting my point? Here it was negative, but it didn't have oxygen. So that's the reason that negative charge was counted along with the valence electrons of carbon. Now here, negative charge is there on the species and you are having oxygen. So you don't have to count that -2 with carbon valence electrons. What you have to do, there are total 3 oxygen atoms. Out of that, you can give only 2 oxygen atoms -1, -1. Na? 1 oxygen you give -1. So there are, out of 3 oxygens, you are having 2 oxygens whom you are going to give O-. And the moment we are having O-, we already have written one point now. O- will make single bond with the central atom. So what you are going to have? Around carbon, basically you are having like this, 4 electrons only, right? And 2 of them, they are O-, and here also they are O-. Now 1 neutral oxygen atom is remaining. So with the neutral, what you do? You make the double bond O. Getting it? Now the thing is, the structure is still not complete because now the surrounding atom are not hydrogen. They are basically oxygen. So you have to complete their octet by using the lone pair of electrons. Are you able to see here? 2 electrons. How many more electrons required? 6. So you need to have 6 electrons around it. Here also 6 electrons, because the thing is already 2 electrons are there. For this particular oxygen, it has made 2 bonds, means 4 electrons around it. So you need 4 more, right? And in fact, from where it is coming, you just check the valence electrons which are present, total valence electrons which are present in the CO3 -2. So total valence electron in CO3 -2. Carbon is how much? 4. 3 oxygens, 18, plus 2 extra electron, you are having 24. So only valence electrons participate in bond formation. So you are able to see how many are there. 4 bond means 8 electrons done. Then after that, this is 6 plus 6, 12, right? So 12 plus 8 is 20 and you are having 24. So all those valence electrons has to be reflected there. What we do is, we tend to forget this dots. And thereupon we lose some marks if at all some question comes on the number of electrons. Are we getting it? So make sure that you are writing this, all of you. And then few example I'll give you. If at all I give you one more example, suppose COCl2. Definitely central atom is going to be carbon. So around carbon, how many electrons? 4 electrons. Now the thing is, there is only one oxygen, that too neutral, there is no charge here. So just make a double bond with that. Two chlorines, make the single bond here using one electron. Now what is remaining? Chlorine, you have to complete the octet. It's already 2 electrons here. Put 1 more, 6 more. Here 4 more. So that's how we make. If you want, you can easily check the formal charge also, right? Formal charge, I have just told you that, okay, you can calculate it like this, but directly when we are putting the negative charge on the central atom, then also it is fine. Getting it? Please draw this, then we'll proceed further. And we are just drawing the structure of it, okay? The thing is, it need not be exactly reflecting the shape of this particular molecule, but that's okay. Yes, are we done writing? So this way we'll be able to draw it quickly. Now let me give you a few. Let us try that. Fourth I have given you now. I'll give you some time to draw. Please draw that. First draw up to this. At least draw 5 to 8, then I'll discuss them. So once you finish off, you are getting any doubt, you can ask, not an issue. Please finish from 5 to 8, then I'll discuss. And once you finish, just write down here, okay, we have finished. Then accordingly, I will get to know that you are done. And please, whatever are the method I'm telling you, you know, so that is basically easier, faster. Only thing is just require little bit of practice. So in case of NH2 minus, I hope people have done this. Yes, what is the problem, Manusha beta? So better don't attend. What's there in it? Okay. Now in case of this NH2 minus, here you see it is negatively charged one. Does it have oxygen? It doesn't have. So basically this electron has to be counted here. So valence electron, or else we say that electrons around nitrogen, how many will be there? Electrons around nitrogen, that will be equal to 5 valence electrons plus 1. So you are having 6, right? Now the thing is, you put like this, 6 electrons around nitrogen, right? Now the thing is, you are having hydrogen here, 1 hydrogen here. Now simply put minus 1 here on the central atom. Getting it? Now in this case, again, you are having nitrogen and there is plus 1 charge. So the electrons around nitrogen is going to be 5 minus 1, which is 4, right? So what you are going to write down, just 4 dots around it. You are having 4 hydrogens also, and just put plus 1 here. Getting it? Did you people draw this or not? Did we draw this? You better clarify the things, okay? Yes? Your structures are matching, whatever I have told you. The thing is, it requires a little bit practice and patience, okay? Now, NO2 minus. Now the thing is, be cautious when negative charge and oxygen is there. You cannot include this negative onto the nitrogen. So what you have to do is, how many electrons around nitrogen? There will be 5, right? 1, 2, 3, 4, 5. Now the thing is, out of 2 oxygen, you can only give 1 oxygen minus 1. So you are going to have O minus connected here. Now the another oxygen which is there, it is neutral, right? So we make this double bond O. Now what else is remaining here? Completing the octet of the surrounding atom, right? So here you are having 1, 2, 3, 4, here 1, 2, 3, 4, 5, 6. That's how the structure gets completed, right? Now, when it comes to PO4 minus 3, again the same thing is, this time again in the phosphorus valence electrons, you're not going to add 3 electrons. What you're going to do is, basically you are having 3 electrons there, and those minus 3 charges has to be assigned to 3 oxygens. So you're having like this, 5 electrons around it. With this O minus, you are having O minus, right? Then there is 1 oxygen which is neutral, so double bond O. What next is remaining? Putting the lone pair of electrons around the central atom in such a way that their octet gets completed. You are having 2 here, 6 here, right? 6. Here also like this. Got it? Did we get this 5 to 8 structure correctly, all of you? 5 to 8, all the structures correctly? And those who went a little bit wrong, did they identify where they have gone wrong? These structures are important. That's the reason I'm discussing it. Because once you are able to draw the structures properly, you will be able to basically, kind of easily identify what is the hybridization. VACPR also become easier. Very good. And you are seeing that you are not taking much time in drawing them. Formals, as I have told you, okay, fine. Just the reason, okay, it is mentioned there, you can check it. And you will get the same charges which are here. Right? So just to save on time, we are just writing down the charges directly. Now the thing is POCl3. Hope people have tried from 9 to 12 also. 9 to 12, have you tried? Now in case of POCl3, which one will be the central atom? Tell me. POCl3. Phosphorus is going to be the central atom. So in that case, how many electrons now? 1, 2, 3, 4, 5. Around phosphorus, 5. Now you are having 3 chlorines, make single bond. You are having 1 oxygen which is neutral, make a double bond. Now next, what is remaining? Putting the lone pair of electrons. Around chlorine I should put 6 because only 1 bond, and around oxygen I should put 4. Right? PCl4 plus. Now there is positive charge. So electrons around phosphorus will be how many? 5 minus 1, 4. Getting it? So you're going to have 1, 2, 3, 4. Why I have done it 4? Because valence electrons minus the charge on that. Then there are 4 chlorines. Like this you can make 4 chlorines. And straight away put the positive charge on the central atom. And you put this lone pair of electron and your structure is complete. Getting it? Now in case of SO2, what you are having is central atom is going to be sulfur and there are 6 electrons around it. And there are 2 neutral oxygen which are there. So make double bond with them. Right? So again, just put the lone pairs around oxygen to complete its octet. Here again, time and again, I am pointing out that basically what you are having is, you are having this particular Lewis structure. You are not drawing the exact shape of it. When it comes to SO3 minus 2, again be cautious, negatively charged and you are having oxygen. How many oxygens you are having? 3. So from that 3 oxygen, you have to assign minus 2, or that means minus 1 to 2 of the oxygens. So around sulfur, this is 1, 2, 3, 4, 5, 6. So you make one this O minus, another one is O minus. Now 1 oxygen is remaining. Please make double bond with that. Now this is the structure. So you just now put the lone pair of electrons to complete the octet. This is what is the structure of SO3 minus 2. Who has got all this structure correct? 9 to 12? Okay, good. Very good. Now, let me give you a few more now. Make these 3 more before we wind up the class. I'm giving you a little bit of time. You can go further. One more I am giving you, NO3 minus. Try to draw for this also. Yes, are we done? Except 13. 13, I'll give you an idea. Here you are having I3 minus, right? I3 minus means I is the central atom and 2 iodines are the surrounding atom there. So in this case, what you're going to do is, I is central atom. In that case, how many electrons around iodine, by the way? Which is the central atom which I am treating? 7 plus 1 because of the 1 minus charge, 8, right? Now there are 2 iodines which are basically the surrounding atom. So you'll be right, kind of 8 electrons you have to show. So 2 electrons you have shown, 3, 4, 5, 6, 7, 8, 3 lone pairs. And then you are having 1 iodine here, 1 iodine here. And just put this minus 1 over it. Around the other iodines, just complete their octet. In fact, you can check also for this I3 minus, this is the formal charge which you have written, okay? Here I, 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now just break this. How many electrons around iodine for the formal charge calculation? 8. How many should have been in its valence shell? 1. How many should have been there in its valence shell? 7. So there is extra of 1. So from there it is coming. Understood now I3 minus? Those who have problem with the I3 minus? Yes? Good. Now, for this xenon, again 8 electrons in its valence shell. Here you are having total 6 of oxygen. Out of that, 4 oxygens will be given -1, -1, 2 oxygen like that. So here you are having 1, 2, 3, 4, 5, 6, 7, 8. So basically 1 O minus here, 1 O minus here, 1 O minus here, 1 O minus here. Then with the other one, double bond O, double bond O. Now what next is remaining? Complete the octet of the surrounding atom. Here 6, here 4. Right? For XeO3, xenon, you are having 1, 2, 3, 4, 5, 6, 7, 8. Double bonded oxygen, double bonded oxygen. Here also double bonded oxygen. 1, 2, 3, 4, 1, 2, 3, 4. Here also 1, 2, 3, 4. Like this it will be. Is it the structure? Yes. Now, when you go for NO3 minus, basically you might have drawn like this 1, 2, 3, 4, 5. You might have drawn 1 O minus. You would have put this double bond O like this. Am I correct? But here be cautious. Reason being, nitrogen can never have more than 4 bonds around it. Remember one point we have written, never violate the octet of second period element, right? So in that case, what you can do is convert one of the pi bond into the lone pairs here. So you are having N around this oxygen, you are having this 6 lone pair. Here you are already having 6, getting it? And here it is double bonded O. Now this one, if at all you calculate the formal charge, you know it will be -1, this one is -1, this is going to be +1 and this is 0. Are you able to see formal charge? N double bond O. Here it is 1, 2, 3, 4, 5, 6. Here also it is 1, 2, 3, 4, 5, 6. Right? When you calculate the formal charge for this oxygen, how many electrons around oxygen? There will be 7. How many should have been in its valence shell? 6. So there is extra 1. Similarly, here also -1. Here also 0. For nitrogen, how many electrons around it for the formal charge? 4. How many should have been in its valence shell? 5. There is a deficiency of 1. So basically, it will be existing like this only because the thing is we can never violate the octet of second period element. It doesn't have vacant 2D. Getting it? So this is the correct structure of it. Especially be cautious with the second period element. Understood? With third period and beyond, need not worry about it. Is this clear? And overall summation of the formal charges is going to be what? This is going to be -1 only. Getting it? Okay, so with this we'll finish off the session, and if at all some of you were not able to do with the same pace which others were able to do, need not worry about it. You just go through the rules and everything and try it on your own because the solution of this is already given to you. And one more point I wanted to stress out, basically why I'm asking you to put these dots, that means a lone pair, because somewhere in JEE they've already asked this question that how many lone pair of electrons are present in I3 minus. And majority of the students, what they have tick marked as only 3 because they considered only lone pair of electrons on iodine. So this is an easier question which has the potential to be asked in NEET also, right? So basically, if at all you ignore these lone pairs, actually answer would have been how much? 9. Getting it? But the thing is, if at all you just focused, question was not that how many lone pair of electrons on the central atom. The question was how many lone pair of electrons in I3 minus. That is the reason there is like, I'm asking you to always put these dots. Did we get the idea? Clear? Is it clear to everyone? Yeah. So thank you and have a nice day.